Okay, so 28.8 millimeter was the width we calculated for RDS-on of 50 milliohm, correct? So, from this we can calculate the gate area and find the gate cap. Okay. Width into L. So, L is width is 28.8 mm into 0.18 micron. How much is this? So, 28.8 into 0.18 into 1000. 5184. So, I will approximate it to 5000. Okay. Micrometer square. Correct. Okay. So, let us say 5 femtofarad. Okay. So, gate cap. I will approximately write it 5 femtofarad per micrometer square. So, total gate cap here is total gate cap, which I will call it C gate, and this was for PMOS. So, C gate P equal to 25 picofarad, correct? Anybody remembers the mu Cox for NMOS? So, PMOS 7, how much? 350, 5 times. So, which means the for the same RDS on, the device size will be 5 times less. Okay. So, for NMOS, mu Cox is approximately 350 microamp per volt square, correct? So, W by L for RDS on equal to 50 milliohm will be 1/5 times W by L of PMOS. So, 28.8 divided by 5, 6. So, approximately I write 6 millimeter. Okay. So, your gate cap or gate area. So, gate cap will be 1/5 obviously. So, we can C gate N equal to 5 picofarad. Okay. So, what is the total gate cap? 30 picofarad. So, CV square F. So, P gate switching loss is C VDD square FSW. This is nothing but C gate. 70 milliohm. Okay. Let me just. Okay. So, I will just write here 70. Okay. So, 30 pico, let us say Now assume FSW equal to 1 megahertz. So this will roughly tell us where exactly we want to, what frequency we want to operate at, because at full load we want to keep this switching loss negligible. Okay, so at 1.2 volt and 1 amp, 120 milliwatt was the total loss. So we want to see how much we have switching losses compared to 120 milliwatt, and then we'll decide whether we can have a higher frequency or 1 megahertz basically is the max limit depending upon how much we get. So P gate SW is 30 into 10 power minus 12 into 1.8 square into 10 power 6. This becomes 30 into 1 10 power minus 6. So you get some micro. So approximately 100 microwatt. Huh? So we still have a lot of margin, which means we can even operate at 10 megahertz also. Okay. So you'll get a 1 milliwatt roughly, and 1 milliwatt is still a very small fraction of your. So I mean, let's say you are targeting 1% of your 120 milliwatt. So 1.2 milliwatt. So 10 megahertz is, I would say, safe side for this if you want to make sure your switching loss is not dominating at full load. So FSW equal to 10 megahertz, your P gate SW will be which is less than 1% of total loss. Okay. Now, what is the other switching loss? So, this is okay for this, but we have one more switching loss, dead time. Okay. So, we have to see if at 10 megahertz that becomes very high, then it will kill your efficiency. So, then we may have to go back and see what are the total switching losses at 1 megahertz and 10 megahertz, then we will finally decide. Okay. So, dead time loss. So, let us say I keep dead time, usually you keep 1 to 2 nanosecond kind of thing. So, let us say T dead equal to 2 nanosecond, okay, and FSW equal to 1 megahertz. So, your P dead SW, how much was that? Anybody remember?
2.52.
No. What was the formula?
2 T1 by TS.
Okay. So, twice because it's
Plus
conducting at both the edges. So, twice into T dead over TSW into 0.7 into 1 amp. Okay. So, T dead is 2 nanosecond, twice divided by, this will become 1 microsecond into 0.7. How much is this? So, if you keep the same dead time at 10 megahertz, that will be 28 milliwatt, which is very high. Huh? So, this will limit your switching frequency or you reduce the dead time proportionally. So, if you do not get less than 1 nanosecond, like order of hundreds of picosecond dead time for 10 megahertz, then it will be very difficult to achieve more than 90% efficiency. So, which means if you are running at a very high frequency, it is not easy to achieve more than 90% efficiency, even if your devices are very fast. Okay. So, that is why if you look at lot of high frequency converters, they are designed either for low current. So, let us say your target current is 200, 300 milliamp kind of thing. So, this will automatically reduce switching losses, then it is okay. But when you target amps of the current, it is not easy to run at 10 megahertz. Okay. So, P dead at 10 megahertz will be 28 milliwatt, okay, which is much higher, approximately 25% of total loss. Okay. So, what will be the efficiency, let us say. So, 150 milliwatt will be the roughly total loss. So, 150 plus 88%. Okay. So, because 25% means of 10% is roughly 2.5%. So, 2% extra you will lose. So, instead of 90% you will get 88%. Okay. So, if you are happy with 88%, then you can go for 10 megahertz. If not, then you have to use a lower switching frequency. Okay. But one thing you have to remember, like when you operate at let us say 100 milliamp kind of current, okay, so then this will start dominating. So, then you have to calculate. So you have to make sure that throughout the load current you have to maintain that efficiency like as flat as possible. Okay, it is not that at peak load of 1 amp you get 90%, and when the load goes, let us say 100 milliamp or so, your efficiency drops to 60% or 70%. That will not be acceptable. Okay, so that is why if you remember that curve, which loss dominates at what load, depending upon that, you have to make sure your switching losses are not that high, that at light load. So, let us say at 100 milliwatt, you lose 25 milliwatt in switching losses total, then what is the point? Like you will, your efficiency will be very bad in that case. So, 75%. So, even though your I square R losses will be negligible in that case, but you have to make sure that this does not dominate. It still remains uh, uh, roughly 10% of your total load. So, when you are operating at 100 milliwatt kind of a load power or output power, in that case if you want to maintain the 90% efficiency, so total loss budget you have 10 milliwatt kind of roughly. So, the 120 milliwatt now is scaled down to 10 milliwatt. So, that 10 milliwatt is the total your I square R plus switching loss. So, I square R loss will automatically scale down because now your load is 1/10 roughly. 1/10 means 1/100 will be I square R losses because it's a square. So, that will not dominate in that case, I square R loss, but this will start dominating and this will limit your efficiency. So, you have to do some exercise. It is not that you choose at one load and just straight away decide and start designing. So, you have to make sure throughout the load current you maintain high efficiency, and that is how you choose the switching frequency. So, your efficiency at 1 megahertz and 1 amp load current I will say at approximately 90% and efficiency at okay. So, these numbers may not be exactly accurate, there will be plus minus 1% error, but that does not matter. You just I am just trying to give you guys an idea that how much basically it will affect your efficiency. So, now at I load equal to 100 milliamp. So, P out is 120 milliwatt. Okay. So, for 90% efficiency, what is the total loss? P loss equal to how much was that? What was the formula? Anybody remember? 1 over?
No, 1 or 1 by 8
Okay.
into P.
Into P out. Yeah. How much will be that? 13 milliwatt?
13%.
Okay. How much is I square R? Into how much was that total RDS on? 120. Why did we keep 120?
No, actually, we fixed that. We found that 90% of that should be 90% of the loss should be conduction loss from that.
No, how much was the total loss? 130, yeah? Okay. So 120 we fixed. Okay, correct. So we had budgeted roughly 12 milliwatt for other losses. Okay. So 0.1 into 120. Sorry, 120 milliohm. How much is that? 0.12 into
1.2 milliwatts.
120 microwatt, huh? 0.12 milliwatt, huh? Huh?
1.2 milliwatts.
1.2 milliwatt? Wait. 0.1 into 0.1 into 0.12. Okay, 1.2 milliwatt. Okay. So now, and your CV square F losses will not change, they will remain same. So 1.2 milliwatt and then 28 milliwatt, 30 milliwatt roughly, huh? So 30 milliwatt of your 120 milliwatt is how much? 25%.
28 milliwatt is dead time loss. That will change.
Oh, sorry, 28 was dead. So how much was that?
CV square 1 milliwatt.
Yeah, 1 milliwatt plus 1.2, and how much will be the dead time loss? That will scale, huh? So what is the total?
That time loss will be 1/10.
2.2 plus 2.8.
So
4 milliwatt.
4 milliwatt. So within 10%, huh? So which means that 100 milliwatt, it's okay. Fine. Now if you go to 1 milliamp, further reduce the load current, then it will start having problem. But usually at 1 milliwatt kind of load current, or 10 milli, 1 milliwatt or 10 milli 1 milliamp or 10 milliamp, you will enter PFM mode actually. So, you will start reducing the switching frequency and you will maintain. So, if you still operate at the fixed frequency, you will see your efficiency curve will look like this. So, if this is efficiency, this is I load. So, usually this is how the curve looks like. It will start dropping at very high load because your I square R losses will start dominating. So, when you go let us say beyond 1 amp or so, it will start dropping because you have designed like 90% efficiency you have kept for 1 amp load. So, if you start going beyond 1 amp, then it will start dropping. So, usually it peaks in the mid load, and then because your I square R losses will be negligible and your switching losses will also not be dominating in the mid load. So, you will see a little bump in the mid load, and then this is your light load. Which may be like less than 10 milliamp or so, you can say. And this, what would happen if you go at, so let us say this is at 1 megahertz, and if I draw the similar curve for, you may see slight change, but here you will see a significant change at 10 megahertz under light load. Okay, at light load it will start dropping. So, this curve actually will start expanding from here itself, something like this. Okay. So, this gap will start increasing as you reduce the load current because your switching losses will be dominating and your conduction losses will be roughly same. So, that is why you see very small change in the frequency, not that much, efficiency. But this is, and if you have, let us say, let me do this. Once you have a PFM mode, you will maintain very high efficiency even at light load because you will start reducing the switching frequency. But if you do not have a PFM mode, then you will get a very bad efficiency at light load. So, for 0.18 micron 1 amp current looks like 10 megahertz is not a big problem. You can easily operate and achieve high efficiency. But now think about let us say instead of 1.8 volt and 180 micron, you go to 5 volt process. 5 volt process means your channel length will also, those devices will have a higher channel length, maybe like 0.5 kind of 0.5 micron. Okay, so roughly 3 times more than this. So, your gate cap will also be, so your switching losses will be 3 to 4 times there. Your whatever is looking like 25 picofarad here, you will see 75 to 80 picofarad there, and this may become very bad there actually for 5 volt. So, that is why most of DC-DC converters, if you see, which are operated at lithium ion battery, like mostly used in the cell phones, and lithium ion voltage we know it is like 2.5 to pretty close to 5 volt, 4.6 to 5 volt. So, this 1.8 volt does not work there, or 0.18 micron does not work. So, you need 5 volt devices, and operating at 10 megahertz there is not easy, like if you want to cater to 1 amp. I mean 90% efficiency is very difficult. You may achieve maybe 85, 86%. So, they are like so far, like if you look at the any product in the market, the targeted current is like 800 milliamp or so or less than that. So, 500 to 800 milliamp and 6 to 7 megahertz max frequency, not more than 10 megahertz is very rare. Okay, but for this particular case 0.18 micron and 1.8 volt input, 10 megahertz you can easily achieve.